Welcome to Ask and Learn.
The domain for this function is x is all real. And if we did want to find the range, it would be, because it's a sine function, from -1 to 1. The intercepts, the first one is 0, 0. And we have another intercept at every pi n, where n is a positive, or n is an integer, 0. There is an odd symmetry to this graph. There are no asymptotes. And if we wanted to know the period, it would be 2 pi. So it's going to repeat every 2 pi. That's pattern. And if we wanted to find y prime, well, we know that this is the same thing as sine x, and bring the 3 on the outside, and we can just do chain rule from here. So that's 3 sine squared x cosine x is equal to 0. All right, and now x, set the derivative to 0 to find critical points. X is every pi over 2n. Oh, my bad. Pi over 2n. All right, and now if we look at our number line, if we make one for the first derivative test, this is f prime, and we have pi over 2, and I'm also going to add in 3 pi over 2, because that's the next pi over 2 value, n, between 0 and 2 pi. So if we test this in the first derivative, test values between anything smaller than pi over 2, it's going to be positive. Between pi over 2 and 3 pi over 2 is negative, and anything after 3 pi over 2 up till 2 pi is going to be positive. So that is our first derivative test. Oh wait, first let's identify that this is, because it's positive, so it's increasing, and then it's decreasing here, so this is a local max. And this is a local min because it's decreasing and then increasing. So that's it for the first derivative test. It's going to be useful for later. And now, if we wanted to find the second derivative for testing for concavity and inflection points, I would take a look at the inflection points, because we know like the general appearance of a sine graph. This is, the general appearance. But we can find the inflection points by looking at y double prime. So 6 cosine squared x sine x minus 3 sine to the power of 3x. And if we set that equal to 0, fine, we will see that the inflection points exist at every pi. And what that means is, let's keep this. This is important information. We'll keep that and put it in the corner. So we have inflection point every pi. And now let's try to graph it. Okay. So let's say this is pi over 2. This is pi. Let's say this is 3 pi over 2. And this is 2 pi. So this is one full period that we're graphing. And we said that we have an intercept at 0, 0. And we also said one at every pi n. So this would be pi n. And this would be the next pi n. And now we said that we have a local max here at pi over 2, 1, and a local min at -1. So the max, pi over 2, 1, and the min for this period is right here. And we said inflection points at every pi, so it's going to change concavity. Well, first we know if this is the max right here, it's going to be concave up at the max. And here, inflection point. And then it's going to switch concavity. And then it'll switch again eventually, but here's the important part, this period. Here we're going to see this is concave up where the local maximum is, and then it's going to slowly switch concavity as it reaches the inflection point. And it's going to switch concavity again at the inflection point. So this is concave down. Sorry. So this is concave down at this point. And then it's going to be concave up as it reaches the min, and slowly going to go back to concave down and then back to concave up. So this is a rough sketch of what the graph would look like.